Okay, hi guys, welcome to our presentation on finding backdoors in applications by Max and I from GovTech Singapore. So this is the brief outline of what we will be covering today. First, a little about us. Max, who will be covering the iOS portion of this presentation, is our resident iOS specialist. He likes digging into mobile applications and poking into kernel level stuff. As for me, I used to be a developer until I found that breaking programs is more fun than making them. Oh, by the way, I just published my first CVE, so check it out. It is 2020-16602. So next, I would like to introduce our organization. We are the Cybersecurity Group, or CSG, of GovTech. So GovTech is in charge of driving the Singapore government's IT systems and technology, while CSG is in charge of the cybersecurity posture for these systems. So as an organization, we believe in giving back to the community. So we will try to publicly disclose any vulnerabilities that we find after working with the developers on it. So we will try to open source any in-house tools or plugins that we develop. So a recent example is a plugin that we built for Google Tsunami that detects the CVE 2020-3452. So this CVE is a directory traversal attack on web interfaces about Cisco appliances. So this was recently submitted and has been merged into Tsunami's master branch. So our guys also recently presented at Black Hat USA, where they showcased an open source intelligence honeypot called Manuka that will help bolster the blue team's arsenal. So if you're interested, do check out the QR code on the right of the slide. So Max and I, we belong to a division named Advanced Cyber Capabilities, or ACC, within CSG. This diagram is a summary of the activities we do on a day-to-day basis. So our bread and butter is we'll generally do pen testing for mobile applications, IoT, and web applications. We also do adversary simulations where we will do phishing operations and we may deploy malicious insiders into organizations to probe for their weaknesses. So in addition to all of that, Max and I also conduct product security assessments. So product security assessments are when we test a product for an extended period of time to make sure that it does what it says on the tin and also to probe it for any bugs. So as the applications that we test can vary widely, from thin clients to web applications to web gateways to black box appliances, we do not have a fixed methodology. So this is an example from a previous application that we tested. So we were supposed to test a web gateway that promised to cleanse all JavaScript from the input source. So we wrote a fuzzer that generated all permutations of HTML tags and their attributes, and we threw it at the gateway. So if it worked, the gateway should pick up all the JavaScript so it will look like the image on the right. So before you ask, yes, we did manage to find a bug where there was a HTML tag and a valid attribute that could result in executable JavaScript. So we have since informed the developer and this has been patched. So now we come to the meat and potatoes of this presentation, which illustrates an incident where we found a backdoor in an application. So we tested this application, which was being used by an agency as part of our routine technical audit. So this application is a critical part of the organization's operations, and it is a mix of native and C# code, and it interacted with a backend database. So users would log in and they would adjust the database and manipulate it by the program's GUI. Okay. So as we were thrown into this program without any background, we started with looking for interesting strings via IDA. So we found a string that said enter password for blank. So this password was not encountered in normal operations and seemed to suggest an elevation of permissions. So therefore it's extremely interesting. So we traced function calls where the string was used and we found that it was being called when the program was starting up. So, when programs start up, they will generally do things like load DLLs, read and write to registry values, initialize data. So this program did all that. But it also did something extra. it will check the keyboard to see if certain keys were being pressed. So this was highly unusual, as most programs don't do that. So we probed a bit further and we figured out what the keys were, and we pressed it when the program was being started up. And voila! The dialog box appeared using the string that we were looking at. This was awesome! So now we have a next question. What is this password? So for starters, we could force the function to always return true using a debugger, bypassing the password check. However, this wouldn't be cool, so we decided to just figure out what the password was. So this was what we knew at that point. The password was not hard-coded because we did not see it in IDA. We did not see it checking any static strings within IDA. So we also didn't think it was stored in the database, as this prompt would appear before the user signs in. And this would be before the application made the database connection. Okay, so after more digging, we found these two functions, generate super secret password and call check password. So generate super secret password would take in a constant seed, as you can see from the first assembly line over there. Then it will generate this password and it will pass it to call check password, which will prompt the user for input and compare the user's input against the generated password. So this is the decompiled code for the super secret password function. So as from the previous slide, we knew that it had a constant seed value. Then it will take that, get today's date and time, and it will do a bunch of operations that involve division, modulus, byte shifting, XORs, and ANDs, and it will return a 6-character string that will change every week. So now, since we knew that the password didn't change that often, we decided to just use a debugger and break after the function ended, so we could get out the generated password from RCX. So this is the password in its full plain text glory. So after we put the password into the prompt, so we were greeted with a console when we started the program. So this does not usually happen when the program starts up. So it's like, yes! So from the console, we discovered that we could run stored database procedures that were previously defined by the developers. So these procedures, they did not have any access control, so our low privileged user could just run any of them. So this one is an example where we could pull out the user logins with the sensitive information like login IDs, company phone numbers, and their login sessions. So what was the impact of this? So a user, by having such a password, can run stored database procedures like what I mentioned, and also raw SQL. So this would let the user do things such as changing passwords for other users and using raw SQL to modify the database, potentially bypassing any application constraints or logging. So why in the world did the developers put that in? So they put it in because they wanted to ease the remote debugging, maintenance, and deployment operations. However, they did recognize that this could be an issue, so they generated this function that will create a password that will change every week. However, since the seed was always the same, somebody with this program could generate this password, which could be used in any installation of this program across any organization. Okay, so before I end my section, I would like to touch a bit on the challenges that we faced when auditing this software. So we were very low privileged users in a very restrictive environment, so we could not patch the binary, nor could we change the underlying OS. So we also had an issue with communicating with the developers. The developers, being developers, they felt that this wasn't a big of an issue because they preferred to go with the ease of development and maintenance. So they did not find having such a backdoor such an issue. So with that, I'll come to a close and let me hand over to Max, who will talk about his experience in encountering a backdoor in iOS applications. Over to you, Max.
Hi, I'm Max. So today I'll be talking about some of the applications that I found on the App Store. So during my free time, I like to look at applications on the App Store, and in this instance, I'll be talking about local authentication bypass, which I found on the App Store. So we actually look at password managers in this instance because password managers hold a lot of safe passwords, and some of them actually are easy to bypass because their verification checks are as simple as string check like true false value. So let me give you an example. This is an example of one of the password manager which I analyzed on the App Store, where the verification of the master password is just by comparing if the string is equal with the input password. So whatever you input is not actually used to decrypt the vault. This allows an attacker to actually use debugger to easily bypass the master password you have set and access the safe password you have set. So we're actually here to see if you can actually entrust your password to password managers that you'll find on the App Store. So as a learning experience, we selected this password manager called Log Password Manager to conduct our test. So it can be downloaded from the Apple App Store, and it has an average of 4 or 5 star with 500 over ratings. So when we first launched this application, it asked us to set a master password for the password manager. Well, I set one, and then after that they asked me to set a password hint, and I didn't set one because I don't believe in password hints. Next, the password manager asks you to back up the master password, and they complains that if you do not back up this master password, there will be no way of accessing the app if you ever forget this master password. Additionally, you can see from the screen, they will double confirm and tell you that there's no recovery passcode. So if you forget your master password, you should not be able to access this application anymore. To analyze this application, our team uses a hooking framework called Backdoors to observe the application flow for this password manager. So I've listed out the syntax over here. So what we want to do is we want to observe the application flow when you enter the right and wrong password. So as you can see here, when you enter the right password, the application will call isSuccessLogin passing 1 as the argument. And then when you enter the wrong password, it calls isSuccessLogin passing 0 as the argument. Looking closer into this function, we see that it's just doing a simple string comparison where it is comparing the input password versus the master password. If both strings are equal, it returns true. If not, it returns false. And then when we look into the assembly code for this section, we see that when you enter the right password, it calls setDateFlag and then calls isSuccessLogin passing 1 as the argument. So we now know that when you key in the right master password, isSuccessLogin will be called with the parameter true, and then it will display all the safe passwords. However, when you key in the wrong password, the application should just only prompt an error saying that you have keyed in the wrong password. But when we look closer to the code, we realize something strange, and that was this application was actually checking for a fixed string, and this fixed string was what you see in the screen *#06**. Well, this was very unusual because if you are actually keying in the wrong password, why would you actually need to check for an additional fixed string? So that led me to actually try out what is actually this fixed string, and we actually found out that there's a secret backdoor in this password manager. So just by keying a user input of *#06**, you write false to the key pair k password on, and it totally removes the need for master password to unlock this password manager. Additionally, as you can see in the screenshot in the right, all your safe password entries are available for the attacker or anyone who has physical access to your device. So they can see all the existing entries that you have on your password manager set. Next, we dive in further to look at this important key value pair on k password on. So we see that this k password on determines if master password is needed to access the app, and k login password stores the originally set master password. And both of these are stored in this group key list file where we actually try to extract it. And extracting it, we found another thing from this application. As you can see in the screenshot in the bottom left, for the k login password, it stores my originally set master password. So this app not only has a backdoor where you can actually access it through the fixed string *#06**. If someone actually managed to get hold of your device, he can also retrieve your master password to unlock your password manager. So much so for telling users to back up their master password and that there's no recovery passcode. When you see that's totally not true. Looking further ahead, we were thinking, Well, this is only one password manager. There are like tons and tons of password manager that you can find in the App Store. So we wanted to look specifically at all the apps that were developed by this developer. So we searched it up and we found 4 applications. 3 of them were actually password managers. So we tried to look at the free password managers, which were Password Manager Fingerprint Lock and Lock Password Manager. So we tried the other password manager, which is called Password Manager Fingerprint, and yet the same interface as the original application we tested. So immediately I tried the same backdoor *hex06 and it worked. So this shows that the developer actually sort of reused the code base. And without testing the paid version of the password manager, we infer that there's a high chance that this password manager would also have the same backdoor. So what would be the impact of this finding is that someone with physical access to your phone could access all your saved password on this password manager, and why would the developer even do this? Maybe because he wanted to have a backup recovery code in case some of their users forget their master password. So as a mitigation, we actually reported to the developer multiple times since January, and as of now, actually the app is still on the App Store. So other than testing iOS applications, our team also looked at a variety of different technologies such as smart locks and IoT devices. So our team would actually publish this variety of security articles on our Medium page, as you can see. So you can feel free to scan the QR code to access a page. Okay, so this year, GovTech will also be organizing a CTF event, and we will be releasing more details on Stack 2020. So Stack 2020 is a developer where the government and the developers come together, where we will share how we can better secure our applications, as well as we will share what the government is doing. And for this CTF, there will be a variety of prizes to be won, including cash prizes. So more details will be released soon. So thank you for your time. You can reach out to us on Angelista and Maxchi at LinkedIn or at Angelista at Twitter. Thank you.